All right, now we're going. Okay, so let me finish this sentence. So why study statistics? You need to be able to understand statistical studies. And that doesn't matter what field you're in. You could be in anything like in healthcare or business, and there will always be statistical studies that you need to be able to understand. Knowing vocabulary and maybe the method behind how a study was done will really help you be able to use that information in your job or your future career. The second reason why we study statistics is to conduct research in your field. So conduct research in your field. And that just means design experiments, collect and organize the data and make predictions. Most of you will go into a field where at some point you will have to conduct research. And it is really good to know how to collect data, how to make sure your data is unbiased, draw conclusions with it, and that doesn't matter what line of work you go into. So it's kind of nice because statistics can be applied to really anything. And then number 3 isn't really necessarily related to your field, but it's to become a better consumer or citizen. So statistics will help you analyze things as just a consumer. So become a better consumer / citizen. And the reason that that's one of these is because by knowing statistics and maybe understanding data that you see or things that you see in news or in media, you can become a better consumer. You can make better purchases. You can understand a little more of like things, like I said, that you'll see on the news. So having a good statistical understanding will help you in that. Those are just 3 reasons why we study statistics, no matter who you are and why you're taking this class. Those are some reasons why. Okay, so now we get into section 1.1, which is descriptive and inferential statistics. So I have a few definitions here to start us off. So the first definition is the word variable. If you've taken algebra or any math class, you probably have seen this word and heard it. So in our case, a variable is a characteristic or an attribute that can assume different values. So maybe your variable is like height or weight, and that can take on different values depending on who you're asking. The next definition is going to be a random variable. And this one's a little different. It's variables that are determined by chance. So some examples of maybe a random variable would be a coin toss. So if you toss a coin, whether you get heads or tails is determined by chance. Another example maybe is the number of children in a family. That's also just determined by chance, how many there are. So that's an example of a random variable. We'll probably get more into those later, but just knowing those definitions is good for now. Next definition is data. And this is just the information we gather with experiments and with surveys. So some examples to get you thinking of what possible data would be. So like, let's say we surveyed some people. So we could ask the questions, how many pets do you have? Okay, if I did a survey and I asked everyone how many pets they had, well, then the data that I collect or the answers that I get, that's my data. So if, I surveyed 50 people that I know and they told me how many pets they had, those answers that I got, that would be my data. Another example is maybe how old are you? So the answers to these questions would give you your data. So like it says, we usually gather this information with experiments and with surveys. So these are just some examples to get you thinking, like people's ages, how many pets they have, maybe your majors, that's all data. And then down here, it says a collection of data values will form a data set. So if I surveyed you all and I asked you all for your majors and I took that list, that would be a data set. So if I took all the answers that I got from everyone, that would be my data set. If I'm doing an experiment on, I don't know, let's see, how many pets people have around my apartment complex. I could ask everyone, get those answers, and that would be my set. Okay, any questions so far? Oh, I see a chat. I like it. Let's see. I say plants definitely count as pets. I would kill every plant that I got. Like I am not a plant person. I fake plants because I can't keep them alive. So I definitely say they count as pets. Like I can keep my dog alive better than I can keep a pet. So, good question. I like it. Okay. Anyone else? Okay. So now we have two main areas of statistics. And these are going to be descriptive statistics and inferential statistics. So I'm just going to write down the definition of descriptive, and this is just from the textbook. So descriptive statistics consists of the collection organization, summarization, and presentation of data. Okay, so that's my first one. That's descriptive statistics, and that consists of the collection, organization, summarization, and presentation of data. So let me write down the fill-ins for the inferential statistics, and then we'll maybe talk about the differences. So just again from the textbook, inferential statistics consists of generalizing from samples to populations performing estimations and hypothesis tests, determining relationships among variables, and making predictions. So inferential statistics is, it consists of generalizing from samples to populations, performing estimations and hypothesis tests, determining relationships among variables, and making predictions. So just to give some examples to maybe help you see the difference between these two things. So something that's good to think about with descriptive statistics is maybe something like the national census. So when they go out and ask you things like, you know, your age, how many people are in your household, stuff like that, they're giving that survey so that they can collect data, summarize it all, and then present it. So it's strictly for the reason, you know, for the purpose of being able to collect information and then just have it's descriptive. It describes what you were collecting the data for, what the data was, and it's just for the purpose of being descriptive, hence the term descriptive statistics. However, inferential statistics is a little different because it has the goal of, you know, generalizing from samples to populations, talking about relationships between things now, and then predictions. So like an example would be maybe a medical study on a new drug or some new medication where maybe you're taking a group of people and you're doing this experiment to see how well this drug works. And then you're hoping to take those results and generalize it to the whole population. So let's say your study comes back and it says that, hey, this new drug works really well. Okay, great. We can generalize that and then actually use the drug for the whole population. So the goal of that study, or, you know, the inferential statistics, aims to actually be able to take something from a sample to a population or something like that. So there's some differences between the two. And you could definitely read in the textbook and get some more examples. Any questions so far? Okay. Something that I mentioned in the definition of inferential statistics was the idea of generalizing from a sample to a population. If you've never seen these words before or done statistics, that might sound a little weird. So let's define the difference between the population and the sample. So just getting these definitions from the textbook, a population consists of all subjects and the book even says human or otherwise. So yes, your subjects or your thing that you were doing an experiment with could be dogs. Doesn't have to be human. That are being studied. Okay, and then the next definition would be sample. And the book defines a sample as being a group of subjects selected from a population. Okay, so once more, a population consists of all the subjects that are being studied, and then the sample is a group of subjects selected from a population. So one of the reasons why we even talk about samples is because it's often too expensive to do a study on a whole population. So instead we do a sample. Like I mentioned earlier, maybe there's a medical study on a new medication or a drug, and you want to see how it performs on a certain group of people. Like let's just say maybe women or something. Obviously, I can't do a study on every single woman in the United States or every single man for that. I just can't. It's too expensive and it doesn't make sense. So instead, we take a sample and we take a group of women or a group of men or whatever, and we do the study only on them. Then we take that and apply it to the population. So when we're doing something, we're always taking a sample. You don't usually do a study on a whole group of people. The only time that you'll see that is with something like the national census, like I mentioned earlier. That's something that we do on the whole population. We ask everyone for that information, but like that's super time consuming and we don't do that very often because of that reason. So part of why we talk about samples is because a lot of the times it makes more sense to do a study on a sample. Like when you guys do your projects and I'll have you come up with something you want to ask a question about or give a survey to people, you're not going to survey everyone in the world. You're going to pick a group of people and have them do your survey. And that would be your sample. So the book gives a nice little diagram. So I thought I would draw that for you guys. So it has this circle. So we'll say this circle is the population. And the sample is a group of people within the population. So if you're struggling to understand the difference between sample and population, I think that diagram really hits it. Okay. Then there's only one more thing to talk about from section 1, and it's just a quick example. It says a researcher wishes to know if a new drug will reduce the number of heart attacks in men over the age of 70. Who/what would be in the population, and who/what would be in the sample. Okay, so population. And sample. So the population, like we defined, consists of all the subjects that are being studied. So if you're concerned about if the new drug would reduce the number of heart attacks in men over the age of 70, Your population is men over the age of 70. That's who you're concerned with. So your population would be men over the age of 70. That's who we're aiming this at, and that's who we care about how this reacts with them or the effect that it has on them. Like I said, we literally can't do this on all men over the age of 70. Doesn't make sense. So we have to take a sample. And the sample would literally just be a group of men over the age of 70 that were selected to test the drug. So your sample would be a group of men over age 70 selected to test the drug. So very, simple, but it's good that you realize that the population is all men over age 70. It's all of them. But our sample would just be some of them, since we can't do a study of every single man. So as you can probably see by now, lots of definitions, lots of key terms and vocab that will be very essential in this class. So definitely in your free time to study the vocab and make sure you understand them. That's a really good study. That is it for section 1, just a very basic introduction, but are there any questions left on anything that I talked about in section 1? Okay. Last thing that we're going to do today is section 2. Section 2 is just one more page, so it'll probably take about the same time that section 1 took. Alrighty, so section 1.1-2, whatever, is variables and types of data. So the first thing we talk about are some types of variables. And there's really, there's two main categories that we break this down into, but then we will break one of them down into 2 further categories. So we have qualitative and quantitative. 2 very similar words, but very different things. So definitions are already in here for you, but qualitative is variables that can be placed into categories according to some characteristic or attribute. So this is something where it's categorical. I can place people in categories or things in categories based on some characteristic or attribute. So some example of some qualitative variables would be maybe your major. So I could take a bunch of people and put them in groups based on what major they are in college. I could also use location. And depending on maybe where you're located, I could place you in groups depending on what city you're in. I could also do this based on gender. That's another one. So those are just a few of them. Those are a few of the big ones that you see. So if you ever thought a survey, maybe they ask you, where you're located, your gender, stuff like that. So those are some of the qualitative things that we use. So it's, like I said, we can place things into categories according to some characteristic or attribute. Okay, and then quantitative is numeric in nature and can be ordered or ranked. So these differ a little bit because they are numeric. So the last one with qualitative, I had major, location. Those things are not numeric. Also, you can't really rank those. I can't say that one major is better than the other. I can't rank them. But quantitative variables can be ranked. So these would be things like age, height, and maybe weight or something. So I could definitely take and rank people based on their age and put that in an order. where qualitative you can't. So think quantitative is numeric and qualitative is more like categorical. Any questions on those two things? Okay, like it says, because quantitative variables are numeric, we can break them into two further categories. Oh no, oh no, sorry, hold on, my screen just shot. Give me 1 second. It looks like my PDF crashed. Okay, one moment. I think we're good now. Okay, should be good again. So, okay, what I was saying was because quantitative variables are numeric, we can break them into two further categories. But like first we have qualitative versus quantitative, but then we can take and break quantitative down. So we break the quantitative variables down into either discrete or continuous variables. Okay, so the definitions are already here. So a discrete variable is a quantitative variable that assumes only whole numbers. So it has a little note right here that I think is really helpful, that discrete variables do not have any decimal values. Absolutely do not. So discrete variables assume only whole numbers and they don't have any decimal values. Okay, then we also have continuous variables. And this is a quantitative variable that can assume any numerical value between any two specified values. Basically, it means that it's measurable. So this one can be a decimal. It can really assume like any numeric value. So some examples just to kind of give you the difference between them. So an example of a discrete variable would be something like the number of students in a class. Number of students in class. That would be something that's discrete because I'm not going to say, hey, we have 9.5 people. That's not how that works. So when you're dealing with like the number of people, that's always going to be something that's discrete. Something else would also be like number of children in a family. Same concept. You're not going to say, oh, they have 2.5 children. Unless you're one of those like statistical studies, it's like each family has like 2.3 children roughly. But no, we don't do that. So number of people is always going to be something that's discrete because you're not going to say you have half a person or something. I love it. I love the jokes. You totally could put someone in half and then you literally have a half person, but maybe we should go with alive people. So like if you're alive. Okay, so the other type of variable is continuous. And this can take on any numerical value. And it says in parentheses, in other words, measurable. That's something that I think really helps when you're trying to maybe distinguish between the two. So an example would be like temperature. So like you could say it's 96.8 or something. So something that could be in a decimal. Like temperature, maybe like the speed you're driving, you could say I'm going like 67.3 miles per hour. It doesn't have to be a whole number. It's something that could be measured. So even like time would be continuous. These can be a little tricky, but next we're going to do a few examples and determine if a variable is discrete or continuous, and that should help really solidify your understanding. So here I'm going to ask for some participation. No shame if you don't get the right answer. This is your first time learning this content, but it's always nice to just hear some voices. So we're going to determine if the following are discrete or continuous. Remember, discrete is only whole numbers, and continuous would be something that could take on any numeric value. So our first one is weight. So, you weigh yourself. Is this a discrete or a continuous variable?
Continuous.
Awesome, thank you. So this is continuous. And I did see some chats. I'm assuming there are more answers. Yes, continuous, great. Okay. This is a little interesting example too. It is age. So what do people think? Would this be discrete or continuous? If I asked you, hey, what's your age? What would you think? A discrete or a continuous variable? Discrete. Yeah, so I got an answer of discrete in the chat, yeah, a few times. So I say discrete on this one for sure. And I say discrete mainly because if I asked you how old you were, you're probably going to say, I'm 25, 30, something like that. Just like I would say I'm 22. However, yes, technically, let's say I'm like 22.8 years old. And yes, perfect, the chat. Doesn't it depend on the unit? It totally does. And that's why I say this one's kind of interesting because it could be continuous if you wanted an exact age. So like if you wanted to know that I am 22 years old and like 8 months or something, like that is pretty specific, or I'm 22.9 years old, something like that. Depends how specific we're getting, because time is technically continuous. So in the usual sense that we talk about age, it would be a discrete variable. Because if you walked up to someone and asked them their age, they're probably not going to look at you and say, I'm 16.73 years old. No one says things like that. So in our usual sense, we say discrete, but a good point to Cameron and Cornelius both, that it does depend on the unit that you're measuring it in. So if you were being exact, it could be continuous. So just wanted to bring that up because it's kind of interesting. All right, and then let's finish it off with one example. So number of car accidents you've had, discrete or continuous? Discrete, perfect. So this one is discrete. So, okay, seems like people are kind of getting the hang of this. And if you look into doing homework 1 part of it, you will see some questions like this, where it just gives you something and asks you if it's discrete or continuous. I don't remember exactly the sections that are covered in homework 1, but I know that sections 1.1 and 1.2 are. So after today, you could definitely do part of homework 1. There'll be questions similar to things that we talked about. But there is one more thing that we're going to cover today. And this talks about a little bit more into continuous data. So since continuous data must be measured. Yeah, I'm sorry. Some of these are a little philosophical here. It depends on how you define time. So since continuous data has to be measured, answers must be rounded because of limits to any measuring device. So obviously, if you look at the temperature outside and let's say it's like 80.5 degrees, well, maybe it's really like 8.47, but your device just rounded. And that's because of limitations. So with any measuring device, there are obviously limitations. We can't go out a million decimal places to be exact. So with continuous data, things do get rounded. And typically answers will be measured to the nearest unit. So like I said, if it's 70.25 degrees out, you might just go with, oh, it's 73 or something. If it's 72.5, oh, it's 73, just because of rounding. So this gets into like what the recorded value actually was of something, and then, oh, what the actual value might actually be. And this is called a boundary. So this word is listed here. And I'm going to write down quickly what a boundary is, just because there's no space on here. Like there was no definition of it, so I just thought I would put it down because I think it's helpful. So the book's definition of a boundary is a class in which a data value would be placed before it was rounded. Okay, just to give you an idea of what the boundary actually is. So it's maybe where the actual data value would be before your measuring device or whatever rounded it. So in this example, it gives you a few things. So the recorded value was 12 inches. So let's say our measuring device had to round, it has to round what it actually measured, and it got a final answer of 12 inches. Well, to look at the boundary, this tells us that the actual value could have been anything between 11.5 to 12.5 inches. I'll explain a little bit how I got this. If you go through reading the textbook, it will tell you, and I'll probably just make a note of this on here. I might write it down here. Let's see. So your textbook tells you that boundaries of continuous variables are given in one additional decimal place and always end with a 5.
Is that, I'm sorry, is that 5 or multiples of 5? Is that, like, you get what I'm trying to say?
Yeah, they do always end in 5. So like, okay, so when our recorded value was 12 inches, so we gave one additional decimal place. Since we started with no decimal places, like 12 inches doesn't have any decimals in it. So we start with 1, and all we did was go down 1. So I subtracted like 0.5. So now I have 11.5, and then I add 0.5. So my actual value could be anywhere from 11.5 to 12.5 inches. And it'll always end in a 5, always, not multiples, just the last digit will always be a 5. And I'll show you that on the next one.
Okay, thanks.
Mm-hmm. So with the next one, it's 0.57 seconds. And like we just said, boundaries are always given in one additional decimal place. So the recorded value has 0.57. So our boundary will have 3 digits on the right of the decimal place, not 2. So I have 0.5, and then I'm going to go down 1. So instead of 7, this is a 6, and then I just add a 5. And this goes anywhere up to 0.575. So you can see it's really just kind of like giving an interval that your value could be from. So if your device recorded it as whatever you're using, recorded something as 0.57 seconds, all it's saying is really what happened or what was recorded could have been anywhere from 0.565 to 0.575 seconds. And it was just rounded. That's all it's saying. So for the next one, it's 3.8 grams. So I have 1 digit on the right of my decimal place. So when I give the boundary, I will have 2 digits on the right of my decimal place. So this becomes 3.75 to 3.85 grams. So all you're really doing is giving an interval saying, hey, even though this was the recorded value, really this is the boundary for what the value could have been anywhere between these two numbers, and my device would have recorded it as 3.8. So if I weighed something and it weighed to be 3.8 grams, it could have been 3.75, it could have been 3.76, and my device just rounded to 3.8. So it just comes into play because continuous data is measured, and obviously there are limitations of every measuring device that you have, whether it's a scale or a clock or, you know, anything that you're using. So it's just good to understand that there are limitations to things and that things get rounded. So even though this is what your device recorded, this is what it could have. I believe there's also some practice with this in the home. Okay, so the last thing on here says to read about how variables can be classified, how they are categorized, counted, or measured using this thing called a measurement scale. And this is on pages 8 through 9 of the textbook. This is just left for you to read. There's just about 4 definitions, I believe. So just read through it today, after class, whenever you get a chance. It's just not something that I'm going to cover in the lecture notes, but it is beneficial for you to know. And if there's anything that I won't cover in the notes, but I want you to do, it will always be printed here. Besides that, I have pretty much covered everything in the notes. So I try not to leave anything out and be one of those people who's like, well, it was in the textbook, so you should have read it. I try to really put everything in the notes. Yeah, that's all we're going to do today. Are there any questions on anything that I covered?
I don't have a question, but I have to go down to the Tivoli to pick up my book because the VA does it some weird way now.
Got it.
But I'm gonna see if we can rent calculators. See if I can help like anybody out or any kind of program or something they're doing for that. So I'll check and then I'll let everybody know.
That's a great idea. Thank you for mentioning that. I know calculators are hard to come by, and there's some also online calculators too. So if we're ever doing a tutorial of something and you don't have a calculator, I believe I can like send a link to maybe an online scientific calculator. So we'll find ways if people can't access a calculator. So thank you, Michael.
Oh, on the subject of calculus, I wanted to make sure, I have one from high school that I had to get for algebra. It's the TI, like it's the Texas Instruments, but it's Inspire CX, and I'm pretty sure it can graph, so I thought it was fine. It just wasn't one of the ones listed, but it's under the same family.
Yeah, I also have a TI Inspire. They're pretty fancy, so yeah, that's like the gold standard of calculators, so you're good.
Okay.
Anyone else? All good questions, though. Okay, well, I'll stop sharing my screen. I'm going to stop recording.